The video is about explaining power analysis. Let's start with the definition of power. Power is the probability of detecting an effect, given that the effect is really there. In other words, it's the probability of rejecting the non-hypothesis when it's in fact false. For example, there is a simple study with drug A and drug B, and that the drug truly is effective. The power is the probability of finding a difference between the two groups. So imagine that we had a power of 0.8 and that this simple study was conducted many times. Having power of 0.8 means that 80% of the time we will get a statistically significant difference between the drug A and the drug B groups. This also means that 20% of the times that we run this experiment, we will not obtain a statistically significant effect between the two groups, even though there really is an effect in reality. There are a lot of reasons that we do power analysis. One is to determine the necessary number of subjects needed to detect an effect of a given size. Note that trying to find minimum number of subjects is not a good idea. Additionally, power analysis can be used to determine power given an effect size and the number of subjects available. For example, if you had 45 subjects available, you want to know if you will have enough power to justify actually doing the study. In most cases, there is really no point to conducting a study that is necessarily underpowered. And finally, doing a power analysis is often just part of doing a good research. A power analysis is a good way of making sure that you have thought through every aspect of the study and the statistical analysis before you start collecting data. So, there is an example about determining the necessary number of subjects. Imagine that you are studying wrist fractures. The null hypothesis is that half the people who break one wrist break their right and half break their left, and the effect size is 10%. And the significant result is if the percentage of people who break their right wrist is 1600 or more, or 40% or less, the alpha is 0.05 as usual. You want power to be 90%, which means that if the percentage of broken right wrists really is 15% or 60%, you want a sample size that will yield a significant result 90% of the time and a non-significant result only 10% of the time. The first graph shows the probability distribution under the null hypothesis with sample size equals 15. If null is true, you will see less than 36% or more than 64% of people breaking their right wrists. As the second graph shows, the sample size of 50 is too small, even if there is a 40 to 60 ratio of broken right wrist to left wrists. But if we make the sample size equal to 270, and we can get a significant result is 90% of the time. So that will be all. Thank you for listening.